All right, so I want to talk about high performance Unity, and this is going to be a little bit of a long form video, but it's still going to be brief and also a practical computer science coverage, so you will be able to apply this right away. I'm going to dive into low level memory, and I'm going to discuss some elements about how we make this faster than ECS. ECS is incredibly powerful, but we can do better. And I want to give you a quick reason why I decided to actually make this, why I dove in and did the research and the effort and the test cases to actually make sure everything in here is working properly. And that is because I'm in a position where I need to support multiple assets, where I need to support assets that are going out to the Unity store or to other places, to various customers, and they need to support multiple versions of Unity and multiple versions of ECS. Now that's a challenge because every single version of ECS destroys the code that works for the previous versions of ECS, which means that typically when you pick a version of ECS, you are now stuck with that version of ECS, because as soon as you get any other set of code or asset that works with that version with ECS, you're tied to those versions. So you have to make it work with your version. And then you can't go pick another version, because it's not straightforward. That is a huge pain point. That means that I would have to spend time learning every single version of ECS and every new version of ECS that comes out to make sure that we can support customers. So I do not want to do that. It's much easier to actually just write your own ECS or just skip ECS altogether when you know how to use the memory structures at a lower level. ECS is probably one of the most dynamic ways to work with memory within the structure of the hardware. Okay, so let's start diving in. Two things. Object-oriented programming encourages poor performance, and performance optimizations encourage poor maintainability. Most anyone with a few years of experience has probably got a good concept of both of these. That the more you focus on object-oriented programming, the less you are near the actual structure of memory and how it is implemented on the hardware. That you get more with Solid, for instance, that I used to be all about. Solid is if I follow Solid, then I am going to have some of the weakest possible understanding of how my objects fit into the structure of a computer. It can be done, but generally that is not what Solid is about. And so for the maintainability that you get from Solid, you lose in performance. For things like websites, where that usually isn't as big of a deal. I've been on countless websites that are like, we'll just throw more servers at it. But then performance optimizations encourage poor maintainability, and that's also true. If there are performance optimizations that I'll show you how to make in this, that if all of a sudden you wanted to make a racing game that instead of just going straight down the track, you wanted to give them the ability to turn left or right, it would destroy the entire physics system, and I would have to rewrite the entire thing. And so there are a lot of things to think about, and if you know your design well, then you can dive further into the performance optimizations right away and design your system around those. Okay, so let's get into an overview of how we do this. We're going to discuss CPU prediction. We're going to go into spatial and temporal memory. We're going to talk about Unity and .NET CLR, their intents and their limits. We're also going to dive lower than ECS. And this is not about algorithms. It's not about math, parallel processing, or GPUs. There's a lot of things that you can do with those that will improve your performance or just destroy your performance. And this is also going to be far from exhaustive just for the low-level memory structure that we're going after. But I will show you how to make it functional and how to start thinking about this. All right, so everything that you've learned from ECS starts out with some discussion of where things sits in memory and some mild reasoning, but I want to make sure that this is really clear. So code interacts with RAM. You get your values, objects, arrays, and structs. And let's say I have 6 different variables, and they're coming from memory from somewhere. And so the CPU gets its instructions and starts grabbing all those variables, and they're all in different locations. Doesn't seem like that big of a deal that they're in different spaces, but RAM is slow. I was conditioned to think about hard drives as slow and that RAM was fast, but that's a reason why we have cache RAM. Cache RAM is actually fast, but still not as fast as a CPU. Think about the Hertz rating on your RAM versus the Hertz rating on your CPU. That should give you a pretty good idea of the speed difference. Okay, so let's talk about what that might actually mean. On every piece of hardware, it's going to be a little bit different because you have different performances of the hardware elements attached to it and different types of hardware attached to it to make it work. So I'm hearing anything from over 100 cycles to over 270 cycles to get one chunk of memory out of RAM. And the other reference up in the corner is a good article that dives into a lot of detailed explanation of this if you want to see more about it. But if you've ever heard that getting a square root, like doing a distance function, is expensive, so you avoid doing it and use square instead of square root whenever possible, that's only 40 cycles. And the thing you're replacing it with is still going to be upwards around like 14 CPU cycles. So you don't really lose that much. But then when you talk about RAM, going out to get one variable is going to cost you 100 to 300 cycles. That's huge. Now, what can we do to make the RAM load faster? Well, one thing is we can put it all in order because it doesn't really matter the size so much. You can grab, if you want to grab 1 byte, if you want to grab 12 bytes, if you want to grab a K of memory, that's going to be about the same. And again, that depends on your hardware. But you can generally expect you should be able to load a reasonable amount of variables within one small chunk of memory and get it out to the CPU in greater than 100 CPU cycles. So I've already just seen, let's just say it was 5 variables, I've just seen a 500% improvement in my processing. That's huge. By just putting my variables in the right order, in sequence, in memory, I have just gotten a 500% improvement in my processing. Now, that's excluding the time it spends on everything else. But if you don't have a computationally expensive process and it's more memory expensive, then this is the perfect place to do this. So we've got it all loading into one chunk, but then we can do more. In fact, the CPU can do more without us. So the CPU has all sorts of intelligence on it about trying to predict. And I'm going to give you one of the basic elements that it has. And that idea is the trust that when we wrote our software, that it was written in a well-organized manner, that our RAM is actually structured in such a way that when I get the first 12 bytes that I'm asking for these 6 variables or whatever it is that they are, and then I ask for, when I go on to the next item in the array, that I'm going to be asking for that next piece of memory and the next piece of memory and the next piece of memory. So it says, well, you know what? It's not going to cost me anything extra to go grab the next 64 bytes or 512 bytes. So I'm just going to grab that all right now. And so it has it. And if your code actually does use that next piece of memory next, then you didn't have to go out to RAM again. And so if you just went through 500 objects that way with only needing to do one RAM load, you have just potentially saved 5 times and made your code 25 times faster. Times 500. So 2,500 times faster. This is what I want you to be realizing about how intense this can have an impact on. Now, at the same time, if you only load like 2 tiny variables, but then spend like 300, 400 cycles in the CPU just processing that over and over again to figure out what you're going to do with it, yeah, then your memory time is not your expensive one. And this is where you need to go to your algorithms. This is where you need to go to your GPU, to other potential sources of how you can improve this. And sometimes what we're doing is just that expensive. Okay, so now let's discuss briefly the concept of spatial and temporal memory. Spatial memory I just went through. Spatial memory is where we're talking about where things are in memory. But let's go into temporal memory. That's time-based, how long something is going to be there. If you have a function that loads some variables up at the beginning, and then you've made your expense to do that, and then you immediately call some functions that go out and call some other functions that call some other functions that are doing a bunch of stuff with memory, and then it cycles itself down and winds back to this area in the stack you're in, and now it's letting your function continue in the code. That piece of memory that it loaded right away might already be gone. So it has to go out and get it again. And again, every time that you're calling out to other functions that are potentially loading up and going through a lot of memory. And so preloading memory in those states doesn't necessarily help. Okay, so that's something to consider. Once you have a chunk of memory that you want to use, you want to keep it in memory and not overload what you're doing in the memory otherwise. So it doesn't have to keep reloading the same piece of memory again and again. And then the spatial memory is just where it's positioned. And now that doesn't just mean sequentially. That can also mean that I know where to look it up in the index. Or in the memory. I'm showing this as like a two-dimensional grid, but memory is just this one-dimensional array of bits that goes on for a long time. And we want to figure out where something is. If I have 1,000 objects in an array, or 1,000 structures in an array, I'm going to go with structures because objects can be stored in different places, even though the array element is just holding a reference to it. Anyway, I want to be able to put those in a certain sequence. So rather than having to say, okay, well, I'm doing something that is near the end of the level. So as long as I have all my memory in order, I could just go grab stuff from the end of the array starting out and not the beginning. Or if I have it granular enough and evenly distributed enough, I could just say, well, I am 60% of the way through this map. So I'm going to start loading RAM from the 60% point of this array. And you just know where those positions for where you are in the map aligns with the physical memory. And now you can just adjust your addresses to get the exact pieces of memory you want, and you don't need to cycle through everything. ECS is really, really good about cycling through everything because it structures it in a way to cycle through that memory effectively. But that doesn't mean you need to cycle through every single object, especially when you already know where things are. All right, so let's dive into Unity, to the .NET CLR, their intents and their limits. To begin with, flexibility is not performance. I brought that up at the beginning, and I'm going to bring it up again, and I'll do it once more. Let's start with Unity. Unity is incredible. I've had a good chance to work with Unreal and Unity, and I have to say that I prefer Unity, but that is largely based on expertise. If I had more time in Unreal than Unity, then it would be the other way around. And that is because of one core truth that you need to recognize. Unity lets you immediately dive into any game type you want. But that flexibility comes at an expense for performance. And just about everything in Unity suffers from this. That means that when you want to make something that is really high quality physics, or that you have some very intense thing for performance that you want to do, or rendering, you very seldom can use Unity out of the box. You have to make changes. Unity came with stuff to be able to have tire and physics, drive car physics. But if you actually want to do stuff, you have to put a controller in that goes on top of it that changes and tunes that physics as you're driving based on the conditions that you're in if you want to actually approach more of a race car style game. Now, Unreal can provide that stuff because they know that is one of the bread and butter products that they sell. First-person shooters and racing games. That's like the key things that they sell. Unity doesn't. Unity is spread out everywhere. And so they give you introduction items for just about everything. And then you're going to need to rewrite pieces of it. You can create a lot of games never stepping outside of those boundaries, and that's fine. But as soon as you want to get into something that is more extensive, something more like AAA, you have to acknowledge that you're going to throw pieces of Unity out and that you will be rewriting them yourself. And that is just fine. I do not want to have to rewrite any of the GPU shader systems. I do not want to have to rewrite burst compiler. that is, I'm not sure anyone would. But then I also, I don't want to rewrite jobs. I've done jobs before. I've done thread processing, and it's not something I would look forward to having to reorganize. It's not where I need to focus my stuff. You let Unity do the things it's good at that work for your game, but then take apart the things that don't and restructure them. All right, so let's go into a specific example. I have a hover racing game, and inside of this hover racing game, we have a race car. It's based on hover physics, so it's not actually using like tire physics or anything like that. It's not colliding with stuff. It is floating, and it achieves this by doing raycasts. It does raycasts out to the environment around it, and it says, hey, how far am I from this point? How far out am I from this point? And it does 28 different points. Now, that could feel expensive if we have a lot of vehicles doing it. And one of the reasons for that is because Unity doesn't necessarily know how far out we need to go. And we could produce a set of memory that can operate at a much faster state because we know exactly how many triangles we actually need to compare against. For instance, raycast of 10 or 10,000. Are you going to be doing a raycast of 10 meters away from you or 10,000 meters away from you? Why would Unity understand exactly what you're going to use that for? It doesn't. It can take some educated guesses as to the intent of how you have your scene set up and what tools and utilities you're using as to how to structure the memory. But in general, it doesn't understand it as well as you do. I know that in this track, I can only go forwards and backwards. That's it. That I can only go one of two different directions. If I go sideways, I fall off the track. And then there's nothing in the boundaries of the world that matters anymore. I reset where the character is on the track and they continue. So in this case, then it is vital that the structure of the track is not set up in a way where pieces are just kind of anywhere, in whatever random order they might have shown up in, but that they are aligned. And not just aligned where it's like this object is next to this object is next to this object, etc. But I need this in slices that make sense to how I'm going to process it. So when I'm processing it, I know that my car is 4 meters long, or none of the cars will be longer than 4 meters, and none of them will look farther than 6 meters ahead. So we are talking about 20 meters distance altogether. That we will not be exceeding a boundary of 20 meters of space that we are looking at any point in time. So that tells me that when I'm looking at my car, I only need 20 meters of memory around me. That is a lot of good processing information, something that I can write something really efficient for. I can fit everything that I need to do that to process all of the physics and for its entire state of the world in one chunk of memory. Very easily. In fact, I might even be able to fit a very large portion of the entire racetrack, possibly the entire racetrack, depending on the size, into one chunk of memory with the cars. So what I need to do is actually take a chunk out of this in slices. So for instance, this corner over here has kind of an angle on the wall, and that holds me onto the track. And there's the same thing on the opposite side. And then there's the two triangles effectively that make up the gap in between. And so from 6 triangles of space that actually overlap, I can identify about a 4-meter region of space. I can identify a 4-meter region of space along that wall. And exactly how that lines up. In fact, with how slow these actually move inside of this game, I can also take other liberties here. I can basically say that, okay, the edges don't need to line up perfectly because we're in hover physics. We're typically at least 2 meters away from the floor of that track at any point in time, or the walls, because the physics keep pushing us off of it to keep a smooth ride. So I know that I can actually make sure that things have more freedom to stretch out even farther, where I could say, okay, well, it looks like I can actually go a lower resolution, and we'll say that every 16 meters is where we're going to be cutting stuff off. And it'll be a little blocky on the physics for corners and where it curves and goes upside down and twists, but that's not going to hurt it so much. Okay, but I get those slices, and now I'm going to be able to get the memory lined up in here so that I just start reading through this memory in order, in sequence, and pull it out exactly as I need it. In fact, the fact that we're going down a racetrack in a very specific order also tells us that memory will continuously go out in that fashion. There's so much power there. Now, this is a specific isolated case, and there's a lot of other ways that you can wrap things, like, for instance, identifying all the general things you'll find within a 10 by 10 meter space. But this is what you need to think about through your video games. Okay, now let's dive into .NET, what some of its limitations and intents are. Okay, so first off, .NET is incredible because it manages the memory for us. It means we didn't need to learn memory management in order to use it, especially for anyone who learned programming through Unity, for instance, and C# in the first place. If you went to college, then you're typically always going to learn about computer science and get farther into this stuff without it. But a lot of people, for Unity, democratizing game development, a lot of the people who get into this are hobbyists. And very few people who get to a senior level in Unity have a real concept of how the memory structures work or how good architecture works and can explain how things fit into there. And so, because many of us started as hobbyists without proper and adequate training. And I'm not trying to say that colleges provide proper and adequate training, because you would be surprised how many don't. But with .NET or C# in specific, we don't need to worry about memory leaks, about pointer math errors, about cleanup work, about having to reorganize memory as we are changing how we're using the memory, because all programs do that, almost all. And we don't need to worry about super bad memory designs, because they do a decent amount of optimization in there. But when we do have that understanding of how to organize that memory, it can be difficult to break outside of the boundaries that .NET has set for us. For instance, unsafe memory, where we get to control it, it does give us that ability, but that messes with garbage collection. It prevents it from being able to tune its memory as good as it possibly could. And it prevents it. It can do a lot of things for locking up memory and preventing compression and preventing reorganization. So we don't want to keep these things around, but then we have to keep these in separate memory. As soon as we're working with memory directly, we are locking up that memory into space. So that means that we cannot directly affect the byte array's positions for long. And we still want to let .NET reorganize things as it makes sense, but we need to balance it. All right. So now to actually start getting into some of the code. The first thing is we're going to turn on unsafe code. Here's the two different places you do it, in an assembly or for the project settings into the player. And we need to mark that it's unsafe. Basically, a lot of these features, even entire sets of function, like getting the memory type and the span type, just are invisible to you unless you have unsafe code activated. There's a lot of features there that are hidden away. But of course, you also have chances to shoot yourself in the foot and destroy your entire project and make it one of the most horrible memory consuming projects of all time. But don't worry, it's usually not that bad. So first thing, how does your memory get organized? This is two different structures. We have an example of that hover physics car. So the car itself I'm going to instantiate it, and it's going to take up 8 bytes in memory somewhere, because this car doesn't actually hold on to the memory of the engines. What it does is it holds on to a pointer. If you're in a 64-bit system, that's 8 bytes, then your pointers are also 64 bits or 8 bytes. That's how I know it's going to be 8 bytes. But that also means that if I move this code over to a 32-bit system, that address will now be 4 bytes. My struct will have dropped down in size. So it's important to understand what OS you're actually building for. And if I'm trying to determine sizes and offsets, then yeah, that 4 bytes really matters. Okay, so I created an instance of car, and now those engines are sitting in an array. It put those engine structs into an array that are sitting together. When you create an array, it puts every element of that array in contiguous memory. That means that it is one after the other with no interruptions. Okay, so anyway, we have the engines, and even though I know I want 4, then it still has to produce that separately. So over here, anyway, so I've got 4 of those engines, and each of those engines has a vector 3 offset and a float power. It knows what the size of a power is, and it knows what the size of a vector 3 is. A vector 3 is another struct. So because it knows those sizes, it can just assign those things into one contiguous group of memory. And that's why all of the engines are grouped together. So all of the offset variables, all of the power variables, those are right next to each other in sequence in memory. But over here, the actual thrusters, another struct that I don't have shown here, that every one of those engines has 7 of these. Remember I said it had 28 thrusters or 28 systems for detecting and applying force, counterforce to the car. So I want 7 of those. That means that every one of those engines is going to have an array of thrusters. So this point of this engine is going to be pointing out to this object or to this array of thrusters. And then the next one will be pointing to this next array of thrusters. And so where those are in memory, who knows? They're not necessarily contiguous. There's no structure forcing it. .NET might put them together, especially when it recognizes continuous things happening in the same structure, or can extrapolate it from what you're trying to do in your code. But when it needs to reorganize memory, it doesn't need to pay attention to this. It doesn't need to try to find a 500K block of memory to reorganize stuff. It can just move smaller elements around to make that work. Now, and there's a bug in this one, but I'll get to that. I'll explain why, because it's actually more efficient than what I'm showing. So this point, I have turned on unsafe, and I'm doing the same thing. Engine struct, I'll call it car. Actually, let's just do this, and let's just say pen, and we'll call this car. Hey, there we go. Yeah, it looks like car. Okay, so that's our car. Remember the structure and how everything was split apart now? So I create my instance, and it creates that 8 bytes. And now that's where I created this little block of memory up at the top. But I made a mistake when I initially wrote this out. I wasn't thinking properly. It understands the exact size, because what I'm doing down here is in public fixed byte. Fixed is something that shows up when you're in unsafe code. But public fixed byte is saying that this is going to be an array, and I get to define the size of it. As long as it is a simple type that is in here. It doesn't want to know it doesn't want to figure this out for how to do it with other existing structs. Honestly, I think it should. It seems a little confusing that it doesn't. But anyway, we're getting an array of bytes instead of an array of engines. And that means that for my engine structure, I need to know the size. So, and of course, to get that size, I also have to know the size of each one of the thrusters, how much memory that takes. So for every one of these, I have to create this constant inside there. I can't use the size of variable because that doesn't work on compile time. That works at runtime. So I have to generate the constants before. And that means I need to know how much memory stuff is going to take. If I were doing something where I had an array, oh wait, do I have an array? I don't. Well, not like this. Anyway, so I've got the sizes in here, and basically what this means is that this engine structure, when I create an instance of it, it's actually going to be one contiguous block of memory for the entire thing. Remember, that was the beginning point of this entire... No, escape. Oh, let's run it again. F5. I was just trying to get back to here. Remember, we were just trying to get our RAM into a contiguous block of memory, like this. I did it again. Okay. So now we've done it. We put our code in this contiguous block of memory. This isn't 2D. Remember, it's again one dimensional, it just goes on forever. So it's all one sequential block. All right. So now that we have our engine structure, this entire thing is in one block. So as we start looping through each of the engines and each of those thrusters, that's not jumping out to memory ever again. It did one load of memory, depending on how much content that takes, which it's 1200 bytes. That's going to take it maybe 200, maybe 300, 400 CPU cycles to load, but it does it one time because it's got the whole structure there. And that means that if I can also take a chunk of memory defining the world around me, like those triangles, and store that in a chunk of memory that aligns, then I can identify exactly which chunk that is, load it up, make one request out to memory for my world environment, and one chunk of memory out for my car, and I can now process everything about that. Everything I need to do for physics check by 2 memory loads. That is an incredible place to be for performance. Okay, so now to do this, I had to use fixed byte, and I had to do unsafe. The struct is unsafe. If you're doing classes with this code, the class has to be called unsafe, or the function has to be called unsafe. And if I'm using fixed byte, then this is largely an unsafe element. It still gets treated as an array externally, but for now, this is, just think of any use of this generally being unsafe. Okay, one other thing. Struct layout. So when you are trying to work with memory very strictly, and as I've told you, .NET will move around objects, and it will move around variable memories, or it'll move around structures to like where they're located in memory. It will also reorganize the structure of your array, of your structure. So what fields go in what order? You don't necessarily have a guarantee on what that's going to be. So putting a struct layout and telling it that it's sequential guarantees that the order will follow the same order as I've written out here. That's important that things actually follow that. There's another one in here called fixed, and with fixed, you can actually define what byte offset things can be. And with that, you can do even more, because you can have a byte array that follows along with these things, and then also have a public fixed, which one was it? Yeah, never mind. It doesn't matter. But it was going to be like a public fixed array size of like types of the actual engine structure. You can have the byte array and this at the same time. And that's important for like dealing with transformations between what you're sending over a network where you need to convert something to a byte array right away. And so that makes things easier. Anyway, how do we get to use engine struct when everything inside of here is actually just bytes? Okay, that is a good question. We're going to create a pointer. We're going to start using C++ or C in C#. This is how. This is the basic concept of how we do it. We're going to create inside of our C# function fixed, and this is like think of it like a while or an if condition. You have your statement at the top, and then you have a block of code underneath it. So we have fixed, and then byte star. That's a pointer. This is how we generate a pointer to a block of memory. And so we're saying, okay, now we're going to get the engines pointer. This is going to be a variable not pointing to the memory, pointing to, like when we ask for it and start using it, it is not giving us the actual engine. It's giving us the address to where it sits in memory. And then here's the actual byte array, engine.engines. This one, engines. So we've got our engines, and we're grabbing the 0 element, because the pointer from a byte array, the pointer from it points to the first element of it, and then everything is sequential after. Because remember, that entire array got put into memory sequentially. Okay, so inside of here, that little and, that and, in this place, I'm working with safe memory. I'm working with managed memory. .NET still put this together. It has it in a spot, and it could still potentially move that fixed byte of arrays. It's really just telling us that we have an array of something and we're going to keep it in here. We can only use simple data types like floats, ints, bytes. Bytes are probably one of the most common to use. Okay, but then we don't want to treat it as a byte. We want this to come out as the pointer. So we are getting the address of, ampersand, a, address of. So we're getting the address of that first byte and using that as the pointer. So now we've got that pointer. We're using a pointer in C#. And then over here, the engine struct. Every time we're getting one of the structures that we're building out of it, we want, if you ask to get a copy of the structure in memory, you say, hey, I've got an engine variable and you've got an engine variable, and I want this to equal that engine variable, engine structure. It's going to produce a memory copy. And so you've got a copy, and if I make changes to that copy, it doesn't matter. It's not going to affect the original unless I copy all of that memory back. But then I'm duplicating memory, putting it in new spots. I have new areas of RAM that I need to access, and this is absolutely not the way I want to go. So anyway, so yeah, in here, I need to be using structs when I'm grabbing pointers inside of there. Now remember, pointer is just a number. It is a 64-bit number on a 64-bit space. It's a 64-bit unsigned integer. So it has no negatives. All right, so inside of here, if I want to grab that engine, I'm going to say that, well, but the pointer for this engine is going to point at the engine's pointer, this first byte of the array. Now, a byte is only 1 byte long, which is typically how we're measuring things here on the computer. But an engine structure, in this case, is 1,168 bytes. And so that's what I worked it out to before. I think I may have changed it, so it's probably a little bigger now. But anyway, so that's 1,168 bytes. That means it's going to go grab, it'll start the structure at 0, at the initial part of that array, but it'll use 1,168 bytes of the array. So if I make changes to variables throughout it, I'll see those same changes come into the byte array beneath it. Okay, so that's how I grab the engine. I'm grabbing the engine by pointing it over at the engine's pointer, which is a byte array. It's a byte star. If I wanted byte stars and to grab a part of this, I wouldn't need to do a conversion. But I'm doing a conversion, so it's because I'm turning it from a byte pointer into an engine struct pointer. So it's how do I treat this memory that starts at this location? And if I want to grab the next position in here, give me a second. I'm going to shrink myself down a little bit. I'm smaller now. Okay. Then I'm just going to go over here to engine pointer, and I'm going to add the size to it. Because remember, this is an integer. This is an integer. Think of it like a number. And so if I want that second one, I need to count out 1,168 bytes later. And now that is my new pointer in memory. It's 1,168 bytes later in the array. And so now I've got the pointer of the second item in this engine array down here. And again, transferring it back out, converting it to an engine struct pointer, and passing it into store it and use it as an engine struct. And again, if I want to get other ones, I'm just going to multiply the size based on the index I want. So if I want to loop through a bunch, it's going to be, I'll say for I equals 0 to 4, or sorry, 0 to 3. And so 0 is going to be 0 times the size of that structure. And that'll mean that I'm right at the beginning of it, because it's also the initial pointer, that first integer, plus whatever the size difference is. And then as I go to 1, it's going to be plus 1,168 bytes later, or plus whatever the next one is. Okay, now there is one more caveat here. You need to know how to use this. And then one more limitation that's going to be pretty important to know. Okay, so we have a fixed byte array. We have the structure for the engine. Now I want to work with the parameters of the engine. I need to use an arrow. I need to point to the correct variable inside of the structure pointer. So that's the key difference. If you're working with managed memory at that time, then you would be using a dot. If you're working with unsafe memory or pointers at the time, then you're working with an arrow. That's really it. That's pretty simple. Now, there's a challenge here with this one. Fixed, getting that byte array pointer in the first place. Remember, this is against a managed object. And that means that garbage collection could be executed at pretty much any point it makes up its mind to. And it'll execute because it's not like it has some specific set of executions that say, oh, just run garbage collection when you tell me to. No, it decides when to run on its own, and that could be in the middle of a set of instructions. But it's managed memory. Every single piece of memory in there, it has information about it saying, well, here's all the different variables in memory that are pointing to it. I have these things stored over in the stack that are using it. I have these things stored in the heap that are using it. And so if I move one of these things over, I'm going to go over to those other two positions in memory and update them as well. And so you can also start to see where this starts to get expensive in garbage collection because of all this memory management it has to run around behind the scenes and do. And so this can get very expensive very quickly. Anyway, let's see. So we don't know when it's going to execute. And because of that, that means that while we are using a pointer in here, if garbage collection moved anything, that pointer would no longer be accurate. And so it's really important that that pins the memory. It tells garbage collection, do not mess with this memory. Do not change it. We are working with pointers here and unsafe code. And so if you change this, you're going to screw up everything we're trying to do. And so it doesn't. It leaves it alone. And that's part of why garbage collection is unable to process things and make it operate as performantly as it could. It can't structure and organize the memory as well. And so when you have this fixed element, you typically just run that in the system where you are operating its repeat loop steps against that data. You don't want to create a pointer and then leave that pointer out there. If you do, that's going to be there for a long time and it can be expensive and painful. And it especially depending if you are on the stack or the heap. If you leave some kind of pointer on the heap and you clear the stuff out and you've got that pointer somewhere else, I'm not even sure what happens at that point. But yeah, you can lock memory in place for too long and the computer never gets to get rid of it while that app is running. And so you've just got these empty spaces of memory that it can never quite deal with. And it also has to do extra thought steps to deal with the fact that you have pinned memory here. Anyway, so hopefully this has been useful. And going back to remember, you're trying to get this stuff aligned, all this memory aligned, when it originally looked something more like this. And that's 6 different calls and down to 1 call to get all that structure. 6 different calls down to 1 call. All right. Anyway, I hope you found this useful. I'll talk to you later.